Hey folks, so like we said earlier, I'm going to be cutting loose a little bit early today for a doctor's appointment. So in this video, I'm going to be going over the most missed questions on the progress check. This is the Unit 3 progress check A on the AP website, and we're going to go over 5 problems here. This not being one of them. The only catch here really being that the radius is 4r, not the 1R or 3R. So that was really the only catch with both of these. You had to kind of recognize what the real radius is, and that always really does go from center to center. And they didn't really kind of extend it to really the center of this guy, which I would kind of raise a little concern with. But College Board gets to kind of do what they want. So that's really that one. We're going to move on to the first real problem, though, and it was the buckets. 2 buckets here. We go from having 2 buckets that have an equal, sorry about that, an equal number of mass in them, and there's some distance d apart. And so if we know kind of at least a symbol for mass 1 and mass 2, we can plug right into Newton's universal law of gravity, and then I just simplified it. And we're going to say that this whole thing is the initial force, what it kind of is in the beginning. Then what happens is half of the water in this bucket gets poured into that bucket. So we still have 2m total of mass. We have just now 1.5 on the left side and 0.5 on the right side. So the total mass hasn't changed, but we've just kind of changed where some of it lies. And it turns out that if you plug this again right into Newton's universal law of gravity, well, 1.5 times 0.5, that's essentially saying half of 1.5 is 0.75. And so it really falls kind of out of the algebra here that we get this 0.75. And then the rest of this is really the same as our initial force. These 2 expressions are the same thing. So we go from having the initial force to now 3/4, because that's what 0.75 is, of the initial force, which seems very odd. I thought this was actually a fantastic question because unless you do the math for it, you maybe would kind of intuitively say that, well, the mass isn't changing, so we should have the same force of gravity because who knows, right? But it's because we're multiplying, it's really dependent on the product of the 2 masses, that this force does actually change. Which is kind of a bizarre thing. It probably explains a little bit for why you don't pull the earth around you, right? Imagine if you had if we dumped so much of the water over here that, or from here instead, that we had 1.99 m, and this was 0.01 m. We could multiply and we would find that this actually would get very, very small. It wouldn't be 0.75 or 3/4. It would get really, really small. So that's really because it depends on the product of the masses, and that is why it's option or answer choice A. Next one here is number 11 about the rotating disc. And so essentially it's saying there's some object, it's stuck on a disc. It's kind of like this question, which is one of our review problems. It's number 3. But instead of the cart being attached to a force probe, the force probe is gone. There is no force probe at all. So the force probe is gone, and really this little car or object or whatever, it's really not a car. It's not going to roll. It just sits there kind of on the bottom. What happens is that as it spins, well, there's friction. So there is a mu of static friction here. So it's essentially stationary on the turntable or the rotating disc, and friction is going to hold it in place as the disc rotates. And we can figure out what the period is. It allows us to kind of set the period, it says. And it's saying which of the following procedures could be used to make the necessary measurements to find the coefficient of static friction. So essentially we're saying, how the heck can we get mu sub s? Well, in this case, since there is no force probe is gone, it's just friction. Friction is going to be the thing that's actually keeping it going in a circle. If this was like a buttery, smooth, frictionless track, and this track started to spin, the cart would actually kind of just initially float just right here in the middle. It would just kind of float in space as the track turns on top of it, like a weird air hockey table or like some trickery. But if there was a tiny bit of friction, but not enough to hold it, the cart would start to spin and then it would just kind of fly off tangent. like we would expect. Like if you're spinning a tennis ball with a string and then the string just snaps, it's going to fly off tangent. And so in this case, friction is going to be our centripetal force. And so we can set the force of friction equal to the centripetal force because it is what's causing, it is that center seeking force in this situation. And so it ends up being that it's answer choice D, but let's look at why. What I've done here is I have actually set the centripetal equal to the frictional force. And then once I just plugged in for friction, we know the friction equation. And I can plug in for the centripetal force. We can kind of do both of those. Well, the m's cancel, and then I would just need to divide by this g and bring it over to the bottom here, and we would have mu sub s alone. And so now we kind of have some equation of sorts. We'd have that mu sub s is equal to v squared over gr. So we would need the speed of the object on the disk, we would need the radius, and we know g by chance already. So if we place the object and measure the distance from the center of the disk to the center of the mass, well, we know the radius. Check, that one's done. Slowly increase the rate the disk rotates until the object begins to slide off. If we know that time and that speed will record the time in which it makes one revolution, well, then we know the period. And we can say that the speed here is equal to, well, the change in distance over the change in time. But in our case, it's going one revolution, so that's 2 pi r. And the time to go one revolution is the period. We already said we know what the radius would be because we'd be measuring it. And if we record the time, we know the period. So we know everything in here, so that we could get the coefficient of static friction. That's why it is option D here. Okay, continuing on. 12 was a great one, but not a whole lot of people missed it apparently. This is literally just an Atwood problem. You could have gone through, found those steps for attacking Atwood machines from last unit, and just literally done step 1 and done step 2. And then you would have just gotten an equation and you would have seen that it had to be answer choice A. It literally just has those only those values in it. Doesn't matter on the tension, but it does matter on both masses. So 13 here, though, this is kind of an interesting one. This one goes directly back to our notes on fundamental forces. Which combinations of particles and separation distances will meet the condition so that the only fundamental force exerted is gravity? Well, we can kind of think about the atom here. You might want to go back, look at that page on fundamental forces. But protons and neutrons within the nucleus, that is not a size range where gravity is the dominant force. Gravity really happens and kind of operates on large scales. So like planets, solar systems, entire galaxies colliding, things like that. Doesn't really happen on this atomic scale. And part of that is because G is this 6.67 times 10 to the negative 11. It's tiny. It's this tiny, tiny value. And so you have to have things on very large scales to have it kind of balance out with this really small universal constant and actually get anything that's like a non-zero or like non-negligible force size. But actually in the notes, by definition, protons and neutrons, that is the strong force. Like that's what keeps them together in the nucleus. Protons and electrons with the same interaction. Well, now we have some range, some distance, not a whole lot still, but positives and negatives, that by definition is the electromagnetic force, specifically the electric part of it. And then we have a proton and neutron located 0.1 millimeters apart. I want to come back to why this is our correct one. And then we have a proton and electron located 1.0 centimeters apart. Well, we have a positive and we have a negative. We're again going to have that electromagnetic force. So even if gravity were present in this one, we still have another force, and we want only gravity. And so even though all these options are like within an atom and kind of a nucleus itself, in a couple of these cases, the proton and neutron, they typically are within the nucleus. It doesn't say they're in the nucleus, though, like in option A. So they're actually located a little bit of a distance apart. And so a proton and a neutron, they're not going to attract each other because they're positives and negatives or anything like that. They're going to attract because there's some distance between them. So they actually will, oddly enough, meet this criteria for Newton's universal law of gravity. There's some distance between them. They have two masses, and there's no other like force that's really going to drive any interaction between them. I would argue that really this is a case where like this force of gravity is going to be so minuscule because the mass of a proton is 10 to the negative 27 kilograms, and the mass of a neutron is also 10 to the negative 27 kilograms. So you're going to have a tiny force of gravity, but it is in fact the best choice out of all four of these answer options. The other ones just have another force present, and this one doesn't. So with that, I think we have one more, and it was not this one. Actually, two more. So this one was what tools should a student use to find the inertial mass? This has to do with kind of those notes on gravity. We talked about mass. We talked about inertial mass is what we used in Newton's second law. This was last unit. And it really is saying that the mass kind of is related to a net force and an acceleration experienced by the mass. Now, in this unit, we've talked really heavily about gravitational mass based on Newton's universal law of gravity again. And in this case, we would call, like, if these were the same one, m here and m here, we'd say that those like are both this. They should be the same mass, but this one we would say is the mass is the gravitational mass because we'd be finding it through using and focusing on gravity. While the second one, the lower one here, F net equals ma, is the inertial mass because it relates really to kind of how much mass there is and how it relates to the acceleration and net force. It has to do with the inertia of the object. So if we want to find the inertial mass, we're really asking about this guy. If that's the case, and I want to find the inertial mass, well, I need F net and I need A. And it's really quite that simple. It was really just thinking, what the heck does inertial mass mean? So in this case, an accelerometer would directly give us A, and a force sensor would directly give us F, and we could just plug in. So that's why it actually is that one. And they really want to use kind of like the minimal amount here. A stopwatch and a meter stick, that's really going to be a lot more excessive than what you need to do. And since it says only select two answers, a stopwatch and meter stick, these would let you get the acceleration, but then you still wouldn't have the force. And so even though those could get A, that is not applicable because of the constraints of the question itself. And the last one, our most missed question, was this rocket. We're told that it accelerates upwards at 2 meters per second squared. That tells us that A is 2 meters per second squared. And I'm already thinking, oh, okay, so that thrust from the rockets is what's causing the net force. So we know the net force is really due to the thrusters overcoming gravity. And so it says that there's no other upward forces on the rocket. Forget about air resistance. That's really convenient. Which combinations of the rocket's mass, m rocket, and force from the thrusters, F thrusters, would result in an acceleration of 2? So they're actually asking us, can you do some math here? Now, I would argue more importantly than being able to like diddle around with the math is really understanding what's the setup. So we know that the net force is equal to ma. We're given the A value. We literally know A is 2. We want to be able to find which pair of rocket mass and thrust gives us that 2 for the acceleration. And so not only are we going to write out Newton's second law, but we have to be able to look at this physical phenomenon. Or if you're like really awesome kind of mental math person, or really just visual, you could maybe think of this in your head. I can't. I have to write this one down. And so I would say that the net force is due to the difference between the force of the thrusters and the force of gravity. And if you really wanted to kind of pause and think about it, if these two were the same size force, the rocket would go nowhere. They would perfectly cancel each other out. They would balance each other out, and there would be zero net force. The net force would be 0. The rocket would go nowhere. A would not be 2. A would be 0 because the rocket would be going nowhere. And so it must be that the thrusters are just strong enough to overcome gravity and give us a net force that results in an acceleration of 2. And so what I've done here is if the left side of both of these is F net, that means I can set the right sides equal. So really I'm actually saying here that MA is equal to all of this. And then I just divide by M, and that's why it's on the bottom here. So now I have an equation for A. I just have an equation for A, and really I can just go and plug in values here now. Because we're given, again, the mass of the rocket. We know gravity is 9.8. And so all we have to do is plug in the thrusters right here and the mass here and find out which of these give us acceleration of 2, because that's what it's asking for right here. That's really the goal. And so this, I would say the hard part probably wasn't going and plugging these in, unless you maybe just stared at these. The hard part was going, this is a unit 2 question. I need to set this thing up and get an equation for A that I can just throw these values into. And that's really it. And we end up finding that only option A and D give us answers that actually are the correct ones that give us an acceleration value of 2. The other ones give us negative acceleration values, which is just unfortunate, because that means that gravity is overcoming the thrusters, so the rocket is going nowhere at all. So that's it. I hope that was helpful. Let me know if you have any other questions, concerns, if I missed a part explaining something, anything like that.